What is up, guys, and welcome back to LaithChem. This is part 2 of our Chapter 1 series. Last video we covered solutions, electrolytes, molarity, and Beer's Law, so if you haven't watched that one, go back because it builds on it. Today we're starting one of my personal favorites, precipitation reactions. Here's the deal. In AP Chemistry, there are 3 main types of reactions in aqueous solutions: precipitation reactions, acid-base reactions, and oxidation and reduction reactions. We're going to tackle them one at a time. This video will start with precipitation, the next video will be about acid bases, and then the video after that will be about redox reactions. Precipitation is actually super visual and easy to cover. When precipitate forms, you see a solid suddenly appear in a clear solution. It's like magic, except it's chemistry, which is better. So without further ado, let's get into it. Now, a precipitation reaction is when 2 aqueous solutions are mixed and produce a solid, the precipitate. The solid comes out of a solution because the product is insoluble in water, so it literally falls out. These reactions are also called double displacement reactions because the cations and the anions swap partners, like a chemistry square dance. A plus B minus mixed with C plus D minus gives you A plus D minus and C plus B minus, where the ions switch dance partners. The color of the precipitate is really helpful for identification in the lab. Silver chloride is white, lead iodide is bright yellow, copper hydroxide is blue, and real chemists use these visual clues to figure out what's in an unknown solution. But here's the key question. How do you know which combination of ions will form precipitate? That's where solubility rules come in, and that's the next slide, probably one of the most important reference tables in the entire chapter. Okay, the solubility rules. Now, you don't need to derive these because they're reference knowledge, but you absolutely must be able to use them quickly, and for AP, it really helps if you have them mostly memorized. Let me walk you through each one. So rule 1, all compounds containing alkali metal cations, including group 1 Li, Na, K, Rb, or Cs, or the ammonium ion NH4+, are soluble, always, without any exceptions. So if you see Na+, K+, or NH4+, it dissolves. Done. Rule 2. All compounds containing nitrate, NO3, perchlorate, ClO4-, chlorate, ClO3-, and acetate, C2H3O2-, are soluble. No exceptions. Nitrates always dissolve. Remember that. Rule 3. All chlorides, bromides, and iodides are soluble except for those with Ag+, Pb2+, and Hg2+. So AgCl, PbBr2, HgI2, those are the exceptions that precipitate. Rule 4. All sulfates are soluble except for those with Hg2+, Pb2+, Sr2+, Ca2+, and Ba2+. So BaSO4 is insoluble. PbSO4 also insoluble. Rule 5. All hydroxides are slightly soluble or insoluble except those containing alkali metals and the group including Ca2+, Ba2+, and Sr2+. NaOH and KOH are the most soluble hydroxides. FeOH3 and CuOH2, those precipitate. Now rule 6. All compounds containing phosphate, like PO4 3-, sulfide, CS2-, carbonate, CO3 2-, and sulfite, CO3 2-, or SO3 2-, are slightly soluble or insoluble, except those with alkali metals or ammonium. A memory trick. The things that are always soluble are like the popular kids: alkali metals, ammonium, nitrates. They dissolve with everyone. The exceptions to the chloride rule, Ag+, Pb2+, Hg2+, think silver, lead, and mercury hate chloride. And hydroxides are antisocial in general, and most of them don't dissolve. Here's a mnemonic or memory aid for the solubility rules. I'll read what's here, and the key is to find something that sticks to you. One classic approach: for what's always soluble, remember NAG SAG. That's nitrates, acetates, group 1, most sulfates, ammonium, and most group 17 halides. For the exceptions, just drill them with flashcards until they're automatic. Another mnemonic that's a bit simpler is SNAP, which stands for sodium, nitrate, ammonium, and potassium. Although this one is easy to remember, it obviously won't tell you every solubility rule, so make sure you keep that in mind if this is the one you choose to take with you. Another approach some people use: build a solubility table on a piece of paper. Rows are cations, columns are anions, and you mark each cell as soluble or insoluble. After you fill it in enough times, it becomes second nature. However, as you choose to memorize these, you may have to make sure that you know them. Precipitation prediction is a core AP skill and appears in both multiple choice and free response every single year. Alright, let's use the rules. For each of these, we need to figure out what products form when the two solutions are mixed and then decide if either product is insoluble. That's our precipitate. For problem 1, we have potassium nitrate and barium chloride, or KNO3 and BaCl2. Swap partners first. You'd get K plus with Cl minus to get KCl, and then you'd get Ba2 plus with NO3 minus to get BaNO3 too. Are either of these insoluble? Well, for KCl, Rule 1 says that K plus compounds are soluble. For BaNO3 Rule 2 says nitrates are always soluble, so there's no precipitate. And this is what we call a no reaction, or an NR. Problem 2, sodium sulfate plus lead-2 nitrate, or Na2SO4 and PbNO3 Swap Na plus with NO3 minus to get NaNO3, which is soluble according to Rule 1 and 2. Pb2 plus with SO4 2 minus, that's PbSO4. According to Rule 4, sulfates are insoluble with Pb2 plus, so PbSO4s are precipitate. For problem 3, potassium hydroxide plus iron 3 nitrate, KOH, and FeNO3 you want to swap a K plus with NO3 minus to get KNO3, which is soluble. Fe3 plus with OH minus gives you FeOH3. Rule 5 says hydroxides are insoluble unless alkali metal is attached. So Fe3 plus is not an alkali metal, and that means that FeOH3 precipitates. This one is actually a rust brown color, so it's pretty recognizable. Now this one is really important. This is one of the biggest things on AP Chemistry, knowing how to write net ionic equations. Here's the concept. When you mix two aqueous solutions, most of the ions are just floating around as spectators. They don't actually participate in the reaction. The net ionic equation strips away all the spectator ions and shows you only the ions that actually react to form the precipitate. There are 3 levels of how you can write a reaction. The molecular equation, which is shown here, is PbNO3 plus Na2SO4 yielding PbSO4 solid plus 2NaNO3 These are the full formulas without splitting. Now, the complete ionic equation is you get this by splitting all the aqueous compounds into their individual ions. So Pb2 plus AQ, 2NO3 minus AQ, 2Na plus AQ, SO4 2 minus AQ on the left. On the right, you have PbSO4S, 2Na plus AQ, and 2NO3 minus AQ. Now, the net ionic equation, you get this by canceling the aqueous ions that appear on both sides. Those are spectators, so Na plus and NO3 minus here. What's left? You have Pb2 plus AQ plus SO4 2 minus AQ, yielding PbSO4S. That's the net ionic equation. The net ionic equation is great because it's universal. No matter what sodium salt or lead salt you use, if the lead ion meets sulfate, you get that same precipitate, and the spectators are irrelevant. The good news about precipitation and stoichiometry is that you already know how to do stoichiometry probably. The only new skill here is that you need to figure out which ions come from which compound and use the net ionic equation as your balanced equation. The steps are identify the reaction, write the net ionic equation, find the moles of reactants, identify the limiting reactant if needed, use mole ratios to find moles of product, and convert to whatever unit the problem asks for, whether that's grams, liters, or something else. Let's work through this problem. We have 1.5 liters of 0.1 molar silver nitrate. We want to precipitate all the Ag plus using NaCl. The net ionic equation is Ag plus AQ plus Cl minus AQ yields AgClS. So step 1, you want to find moles of Ag plus. The moles is equal to the molarity times the volume in liters, which is 0.1 times 1.5 to get 0.15 moles Ag plus. Next step is that you want to use the net ionic equation and use the mole ratio of Ag plus to Cl minus, which is 1 to 1. So we need 0.15 moles of Cl minus since the ratio is 1 to 1. Step 3, the Cl minus is coming from NaCl, and NaCl gives 1 Cl minus per formula unit. So we need 0.15 moles of NaCl. Lastly, you want to convert to grams. The molar mass of NaCl is about 23 plus 35.5 equals 58.5 grams per mole. The mass is 0.15 times 58.5 equals about 8.775 grams of NaCl. That's your answer. Not so different from regular stoich, right? The key new move is going to be going through the Net Ionic Equation and making sure you're counting the right ions. So here's your cheat sheet. The 5 steps for any precipitation stoichiometry problem. Screenshot this if you need to. 1. Write the Net Ionic Equation. 2. Calculate the moles of what you've been given. 3. Check for a limiting reactant. If you're given amounts of 2 reactants, one of them runs out first, and that determines how much product you get. 4. Use the mole ratio from the balanced Net Ionic Equation. And 5. Convert to whatever units the problem asks for. The limiting reactant step is where most students lose points. If the problem gives you 2 reactant amounts, you must check which one is limiting. If it only gives you 1 reactant, assume the other is in excess. Now pause the video and try this one. This one has a limiting reactant, I promise. Come back to me when you got an answer. Ready? Let's go. First, identify the reaction. AlNO3 and KOH swap partners. Al3 plus meets OH minus to yield AlOH3, and K plus meets NO3 minus to yield KNO3. KNO3 is soluble according to rules 1 and 2. AlOH3s are precipitate according to rule 5, which is that it's not an alkali metal hydroxide. The Net Ionic Equation is Al3 plus Aq plus 3OH minus Aq, yielding AlOH3s. Now for the moles of Al3 plus is equal to 0.05 liters times 0.2 molar, which is 0.01 moles. For moles of hydroxide, you have 0.2 liters times 0.1 molar equals 0.02 moles. Find the limiting reactant. From the Net Ionic Equation, you need 3 moles of OH minus per 1 mole of Al3 plus. So for 0.01 moles of Al3 plus, you need 0.03 moles of OH minus. But you only have 0.02 moles OH minus. That means OH minus is the limiting reactant. The moles of AlOH3 produced is equal to 0.02 moles of OH minus times 1 mole of AlOH3 divided by 3 moles OH minus to get approximately 0.00667 moles. The molar mass of AlOH3 equals 27 plus 3 times 17, and that's 78 grams per mole. The mass is 0.00667 times 78, which is about 0.52 grams. That one's tricky. The limiting reactant step is what makes it an AP level problem. Great job if you got it. And this, dear viewer, is where I wrap up the video, and I wish you all well. Even if you're still struggling, I hope this video helps you understand at least one more thing about precipitation solubility that you didn't know before. In the next video, like I mentioned, we'll start to briefly talk about some of the more acid and base stuff, including titrations and the basic reactions. If that's something you're looking forward to, then make sure you subscribe to the channel and like the video. I'll see you in the next part. Thank you for watching.